In this work, our goal is to evaluate classifiers' robustness to possible changes in input distribution. To do this, we exploit the meaningful features learned by generative models. Surprisingly, we find that standard adversarial training against pixel space perturbations doesn't improve robustness to high-level semantic changes, and in fact makes things worse. The problem we're concerned with is distributional shift. Because the world isn't static, and there are always limitations when collecting data, we can't be sure that our models will encounter the same distribution of inputs during deployment as they were trained on. While we'd like our models to correctly generalize to all new inputs they encounter, in reality we know that they are too often confidently wrong. There has been a great deal of attention on one instance of this, so-called adversarial examples. And there has been useful progress, with some techniques such as adversarial training improving classifiers' robustness to these bounded perturbations to pixel values. But there is no realistic situation, either due to an adversary or a natural distributional shift, in which these pixel space perturbations could be encountered. So how relevant are pixel space perturbations to achieving robustness in a sense we actually care about? In our view, there should be more focus on methods that have clear relevance to real-world concerns. For some useful intuition, consider a neural network that classifies images. The whole promise of deep learning is that these networks learn a hierarchy of features. Low-level features are learned from the pixels, which are in turn composed into increasingly high-level, meaningful features. Now consider a generator network that has been trained to take a random input code and output the pixels of a realistic image. It too learns a hierarchy of feature representations, but in the reverse direction to a classifier. Activations early in the network encode high-level features, and the further on you get, the finer the granularity of the feature encoded by each activation. In our setup, we use a pre-trained generator network to generate images that are then classified by the classifier. Note that if we wanted to, we could perform a perturbation to the pixels of the generated image. But instead, our method is to perform perturbations to the activation values inside the generator network. By perturbing the activations at layers throughout the generator, we can affect meaningful features of all granularities in the image that is output. Once an input code is fixed, we can simply use backpropagation to find the perturbations to the activation values, such that the classifier gives the wrong answer for the generated image. In this example, the generator at first outputs the volcano image on the left, which is correctly classified. But we can find small perturbations to the generator's activations that gradually change the volcano until the classifier labels it as our target class of goldfish. The middle image shows the difference made by the perturbations. In this case, there are high-level changes such as the volcano erupting more explosively and the addition of a rocky outcrop in the foreground, and there are low-level changes to the textures of the forest and clouds. We can verify that the different layers in the generator do indeed encode different kinds of image by seeing what happens when we restrict the perturbations to only certain layers in the generator. Here we can see that perturbing the first 6 layers affects high-level features, and later layers affect increasingly fine-grained features. In these examples, we can see the wide range of meaningful features that can be perturbed. The position of the water snake, the shape of the mushroom, the colour of the dog's fur, the texture of the foliage, and the contents and structure of the bookcase. We evaluated 4 pre-trained classifiers, including the ImageNet state-of-the-art. 2 models, shown in red, were adversarially trained to be robust to traditional pixel perturbations. Here we can see that for all 4 models, for over 80% of images, only a small perturbation is needed to find a meaningfully changed example that the classifier gets wrong. So the classifiers are not robust, as expected. If we restrict our perturbations to only the final 6 layers in the generator, then we affect only very fine-grained features. In this case, as we might expect, the pixel-robust classifiers require larger perturbations before they output the targeted incorrect label. If instead we restrict our perturbations to only the first 6 layers in the generator, then we affect only high-level, meaningful features. In this case, we can see that the pixel-robust classifiers are much less robust than the standard models. This is surprising because the intention of adversarial training is to create more robust models, not less. But our work suggests that this may actually harm robustness to variation in the meaningful features that are actually present in the data. In summary, we perturb the activation values in generator networks as a way to evaluate classifiers' robustness to meaningful feature changes. Our finding that adversarially trained models are actually less robust in this sense is surprising and seems worthy of future investigation. Do consider reading our full paper if you're interested in learning more, and please do ask if you have any questions. Thank you.